right, you should be able to see my screen. Thank you so much, Jim, and the GDG Southlake organizers for having me. I'm particularly excited to speak anytime about service mesh and what's happening in the space. I've spent a lot of the previous three, actually no longer, 5 years in the service mesh ecosystem, and helping people try to solve real problems with it. And although the service mesh pattern and some of the technology has been around for at least 5 years, it originated a lot of the patterns that we're seeing in the service mesh space originated at places like Google and and a few other companies. But what Google had and deployed in their infrastructure and what got open sourced are completely different things. So now the technology that exists in open source, which has been maturing over the last 5 years and continues to, once you put it into a real environment, that's when you start to learn about the maturity of a technology like this, areas for improvement, and what sort of the things that you need to either have in place or new opportunities that pop up because of technology like this. So I'm going to be talking a little bit about those topics today. I would say the talk will be broken up into 3 main sections. One, I'm not going to assume that everybody is familiar with the service mesh, so I'm going to give a quick little intro to that. The second section will start to dig into some of the areas where innovation is happening and how that affects the future of the service mesh. And that, we'll start to see the different areas of the mesh, like the data plane, which I'll define in a second, or the control plane, what those things enable, and what the future that we're heavily invested in here at Solo, and I'll describe what we do here at Solo in a second. But this is a very interesting space, very interesting to us, and we're helping to push the market forward in this area. So as Jim introduced, my name is Christian. I'm based in Phoenix, Arizona. I used to fly a lot back in the travel days, I guess, a lot through DFW. I was before I was at Solo, I was at Red Hat, and I worked with a lot of the early adopters of Kubernetes. Before that, I'd worked with Amazon.com and Zappos.com back in 2011, 2012, when they were in the middle of, Zappos specifically, in the middle of migrating their monolithic application to, it wasn't called microservices back then, but a services-oriented architecture that actually was running in Amazon.com's e-commerce platform. So it was a migration. It was a move to cloud. It was a monolith to microservices adventure. All of Zappos.com back then was written in Perl and Bash scripts and MySQL, and the front end of Zappos.com, what consumers see, the back end, the inventory systems, all of that stuff was written in basically Perl, and that had to be slowly evolved because it's a running business. By that time, Amazon had acquired Zappos. It was a running business, but so we had to slowly split out the different pieces into services, migrate part of that to AWS, and so that was before Docker and Kubernetes, all this stuff. But when the open source technology came out to support an operation like that, the packaging of software with Docker and Kubernetes to manage the scale out and so on. The parts that were still interesting to me were, how do these things connect? How do they find each other? How do they stay resilient? How do we secure the connections? And that's where I got involved in the service mesh, in Envoy Proxy initially, and then in service mesh. And at Red Hat, I actually helped bring the Istio technology into Red Hat. And then for a few different reasons, um, I had an opportunity to go to Google and work on Istio and Service Mesh full time. But at the last second, I chatted with the founder of Solo, and we saw an opportunity for a much bigger market than at least the way Red Hat saw Service Mesh, and maybe even Google. But we saw a much bigger market opportunity, and so I ended up at Solo. Now I've been here for almost 3.5 years, and we are a service mesh and modern application networking company. And so a lot of the stuff that we're doing is working with customers, working with people who are actually deploying this at scale, and solving a lot of those challenges with the technology, and we're solving a lot of the problems around it. So, and I'll talk a little bit about that as well. Like I said, so Solo's been around actually officially for 5 years now. Recently, we raised our Series C at a unicorn $1 billion valuation, and we focus on this problem area. How do services, especially when you start to modernize and go to cloud environments, how do those connect, and how do we secure them? How do we apply policy to them and keep that policy consistent? So you can think of it as a layer on top of your applications once they've been deployed. And how do we solve these problems for any applications? And so we like to say that we're focusing on abstracting the network and simplifying. When people deploy microservices, to probably have already existing landscapes of services that have been deployed in VMs or whatever, and different versions of VMs, different networking abstractions like SDNs and other overlays, firewalls, some on containers, some on-prem, some on maybe a public cloud, maybe even functions as a service, throw that in there. Now, how do you solve those problems that application developers and SREs, DevOps folks need to worry about around high availability, around security, around fault tolerance, consistency in policies? And so that's where we come in. Service mesh is part of that solution. In the past, how did people solve these problems? So, you might be familiar with the enterprise service bus, or even more recently, kind of API management. But that's not the only way people would solve these connectivity problems or service to service connectivity problems. They would actually write a lot of this stuff into the application code itself. Right? Things like timeouts and retries, circuit breaking, these were baked into the applications. Rate limiting, certain security enforcements, JOT token checking, this type of thing. We would write these into the application. And in a world where we're trying to adopt cloud technologies, containers, Kubernetes, public cloud, whatever, and we're building that CI/CD pipelines and observability systems around it because we want to be able to move faster. We want to get changes from developers' laptops out to production faster, so we can get things in front of customers and get feedback and understand whether or not that provides any value. Right. And so if we're trying to move faster, one of the things in that in that direction is, if we have a lot of these policies, shared policies about how services are allowed to or supposed to talk with each other, and we need to make changes to those policies, going back to the developers and asking them to change their code is, that's slow. That creates bottlenecks. In the past, we tried to centralize a lot of those things. So that's where the ESB, API management, that's why we tried to put, even further back, we tried to do everything through message queues. So centralizing things allowed allowed some of the management teams or the policy teams to kind of try to control what does high availability look like, what does retrying and service discovery, and what does that actually look like, and we can control it from a central location. This, however, doesn't fit very well in that decentralized model, self-service model. Here, we got to move quickly, make changes independently of other teams, right? When you have to go and open tickets and talk with the API team and, hey, I need to change the routing to this, or this needs to be tuned for this application. Whenever you have to centralize and synchronize, that slows things down. And that's from a people process standpoint. But from a technology standpoint, you can imagine forcing everything through some centralized bottleneck piece of technology that has all kinds of other effects. The idea that if something happens to that shared infrastructure, that affects everyone, not just the application that may have taken it down. Right. So you have the noisy neighbor isolation problems. You have the shared fate outage problems. So from a technology standpoint, and then scaling this, getting this into other environments, at least with the technology we've seen in the past, becomes pretty difficult. And so the pattern that the service mesh brings is, why don't we decentralize the enforcement and implementation of these policies, of these application networking policies, like service A can talk to service B, but only so many times a day. Or service A can't talk to service B if B is deployed in the public cloud. End user, John is making a request to service B through service A, but user John can't see, these certain methods on the API. So controlling those policies, exposing those policies, but doing that in a way that pushes the enforcement down to the level and granularity of the application, and not through some centralized thing, or leaving it up to the development team to hopefully get it right, and then maintain the changes as service change, the evolution of life cycle of the service. What if we could take the engine or the implementation of things like service discovery, load balancing, rate limiting, distributed tracing, retries, circuit breaking, these types of things, and put them into a reusable asset or a reusable piece of infrastructure that we can then scope down to the level of the application. And we can configure that remotely outside of the application. This, gives us a little bit more fine-grained control over the behavior of these policies. If this asset or this proxy goes down, it affects maybe an instance or one service, not everything. We can write declarative policies about what should happen, and store those in Git and enable self-service around that, and come closer to a cloud native model for describing this behavior, and then apply it and change it dynamically, quickly. Maybe service B has been compromised. We need to change the policies, the security policies, routing policy, all this stuff immediately, without having to go back to the developers and saying, hey, do you mind making this change? So, at scale, what this looks like is, more of these enforcement points deployed with the application instances. So in a highly decentralized approach. But you still have to balance that out with, if you have all these moving pieces, you have to manage them somehow. You have to configure them. You can't expect to, configure these by files and logging into servers and making changes on the system and doing hot reloads, that kind of stuff. So The rest of the infrastructure to support this needs to kind of be centralized. You have to have that balance between, all right, the enforcement point and the scope is down to the level of the applications, and there's no centralized bottlenecks. But we still need to be able to manage this system, especially when we deploy tens, hundreds, thousands of services across clusters, multiple clusters, VMs, on-prem, public cloud, and you need to be able to, very quickly and efficiently manage this. And so that's where, a large-scale deployment of a model like this becomes more. I mean, the service mesh is definitely part of it, but there's more things that you have to solve around it. And how the service mesh evolves and the things that we can do and that become, opportunities because of an architecture like this are the things that we would expect to discuss when we talk about the future of service mesh. Because as more and more people adopt an architecture like this and start to see the value, the more opportunities there are to make use of this this abstraction that we're building on top of the network. So let me pause right there. Let me just go see whether there's any questions real quick. Thanks for the observation about the bourbon collection in the background. But feel free to ask any questions. What do we have here? Somebody asked about Bridge and WebAssembly. Okay, so we're going to get into a lot of this stuff as we go along here. All right, so that was kind of the intro. That's service mesh is a pattern, is a piece of technology as well that helps to decentralize the policy enforcement of APIs and services that have been deployed, ideally anywhere. It shouldn't matter where they're deployed, but if they connect over the network, then we should be able to apply some consistent policies. Now, the service mesh architecture itself is built on those proxies which live with the applications and enforce application-specific policies, and the control planes, or the part of the system that dynamically configures those proxies. Right. So the data plane is where the proxies run. The requests are going through when an application talks to another application, like we had in this diagram. Application, that request or those messages flow through the proxies on the originating end, as well as flow through the proxies on the terminating end. And we can enforce routing, security policies, rate limiting, this kind of stuff in the proxies on behalf of the application. That's what we call a data plane. Those proxies that make up that part. The control plane is the piece that's also connected to each of these data planes, these proxies, and configures them. The end user might describe some declarative configuration and gives that to the control plane. The control plane does a translation and pushes that out dynamically to the proxies. So, not surprisingly, that's the architecture of service mesh, and not surprisingly, the future of service mesh has something to do with both of those pieces. The data plane, which we'll talk about next, and how that can be used to kind of push some of the innovation in this space around extensibility, especially around optimizations. You have all these proxies running everywhere. There's areas for optimization, and there's a few things that we can do to enable new ways of communicating with the services as well. So we'll talk about the data plane first, and then we'll talk about what does this the future of service mesh look like in terms of the things that you can build on top of it, on top of the control plane. So if the control plane gives you this abstraction in terms of how to manipulate and program the network and the behavior of applications in the network, then what can we build on top of that? to automate things like canary releases, as an example, or things like intrusion detection and correcting of scenarios that that might be taking place that you don't want, or debugging when things go wrong, when services misbehave or requests come in or failing. How can we debug and very quickly understand how to correct that? So we'll go into some of the innovation or what the future would look like on top of the service mesh as well. So let's jump right into it. This is actually the future and the data plane and the evolution of it is actually something that I talked about quite a while ago now, back in 2019. Where at Service Mesh Con, I talked about this, the data plane actually being a spectrum. We talk about it in terms of a sidecar proxy or a proxy that lives with the application instance and helps it along. But it doesn't have to be just that model. So at one extreme, we can implement the behavior, this application networking behavior, in the code itself. Now, generally, we want to try to not do that because there's a lot of operational overhead and challenge with doing that, especially when you support more than one language. So implementing things like timeouts and retries and circuit breaking, service discovery, load balancing for, let's say, a Java application is doable, right? And actually, a lot of companies did this. But then when you start to, I remember at least back when I was developing, you go from one, let's just stick with Java for a second, one type of threading model to maybe asynchronous or non-blocking model. Now the implementation of load balancing and circuit breaking, these sort of things change, right? And now you extend that out to Node.js. Now that you can't reuse the Java stuff, you have to find the Node.js equivalents for solving these problems, and then Golang, and then Python, or whatever other languages you might want to support. So operationally implementing these, hoping that they're implemented exactly the same. There's nothing worse than not being able to understand the system because the implementations are so widely different when things go wrong. All right, now hope that they're exactly the same, and that in the developers that are using them are going to use them correctly and implement things consistently. And then if there are bug fixes and other patches that need to be made, rolling those out to all the different languages, all the different applications, hoping the developers apply them correctly. I mean, there's a lot of uncertainty there. So, going away from implementing a lot of this logic in the code is probably useful for a lot of scenarios. Now, not all, because there definitely are some very low latency, requirements around some of these applications that you have to have that all of the things in the code itself, and you can't take maybe a couple milliseconds extra hop in the proxy in a sidecar proxy to do that. So that's one extreme, doing it in the code. The other extreme is forcing everything through a centralized shared gateway, and then there's the spectrum in between. There's optimizations in between. A lot of the service mesh implementations you'll see are have a sidecar proxy model, and from there, we can discuss what are the pros and cons of some of these other options. But back in 2019, there were hints of these directions, right? It wasn't actually fully fleshed out in the implemented in code scenario. The gRPC libraries were starting to implement some of the control plane APIs, or to be able to consume some of the service mesh control plane APIs so that they can participate directly as a first-class citizen in the service mesh. And same with some of these other models. But that's what we're going to take a look at a little bit more. So a very popular data plane or a very popular proxy that a lot of the service meshes have opted to use because of its performance, because of its power, its feature list, is Envoy Proxy. And Envoy already happens to be kind of where the innovation in the community is happening. So if you want to look at the future of service mesh, look at Envoy. And you can see things like WebAssembly being introduced. So this enables extensions. You can see things like HTTP3 being introduced, or things like the API used to serve Envoy's configuration dynamically actually being pulled out and used in other places, like we saw with gRPC. So Envoy already has a lot of stuff happening around it. Now, at Solo, we recognized the opportunity to continue to extend Envoy to support additional protocols. So gRPC, HTTP, 1 and 2, HTTP3 now, some of the database protocols, Kafka to some extent. But we also wanted to support, the federation of data across multiple services. And so GraphQL has a nice protocol for that. So extending Envoy Proxy to understand GraphQL and leverage the rest of Envoy's powerful routing engine to achieve things like call orchestration and data aggregation from across a fleet of services. This becomes a pretty powerful way to interact with your services. And I'll talk about that a little bit more in a second. But then down lower, below Envoy, and the way the networking stack ends up working, we can extend that functionality with a technology called eBPF. And there are things we can do on the networking path to optimize how packets are moved between the network devices, between the user space proxies, in this case Envoy, and between applications, especially in a sidecar model. eBPF can be used to optimize that, to scrape data and information about what's happening for observability, and used to tie in with some of the layer 3 and layer 4 policies that you might already have on the network. Envoy and the service mesh typically is operating more at layer 7, but can we combine and get unification between those sets of policies? And eBPF becomes helpful for that. So, for example, the Istio service mesh uses Envoy Proxy, and you can see that in this diagram, the Istio proxy. What is it? It's really base vanilla Envoy with a few extensions, a few filters that have extended Envoy, mostly to provide a way to extend Istio's telemetry data, as well as a way to exchange information between sidecars at runtime in the service mesh. Now, there's other things like we built at Solo that put more functionality into the proxy, things like request and response transformations, especially in a gateway use case. This becomes pretty important. Things like web application firewalling, capturing proxy latencies, these types of things. But then we've also built GraphQL directly into the proxy, which then enables that model, like I said, that enables Envoy, wherever it's deployed, to aggregate and federate calls to backend services and retrieve just the data that is needed by the client following the GraphQL protocol. Moreover, we can configure this with a declarative configuration instead of going and actually building a GraphQL server by hand to do all this stuff, and then realize as you're building it, oh wait, I need rate limiting, I need auth Z, auth N, I need caching, I need all of this stuff that might already have in Envoy, in a proxy built to handle traffic like this. All right, so extending the data plane to be more expressive, to support more clients, and to pull data from multiple different sources makes Envoy, whether it's running at the edge or in the sidecar, a lot more powerful. And so this is just one example of leveraging the data plane to kind of push the boundaries on what service-to-service communication needs to look like. Another area of the future of service mesh, where things are going and where we are helping to push it, is in optimizing the data plane. We saw, let's see if I can remember what that would be this slide. All right, we saw this slide. Now, there's a lot of control and a lot of flexibility that we can get from an architecture like this when we have the sidecar proxies running with the application instances, whether that's on VMs or containers or wherever. There's a lot of control that we can get. But we also pay a lot in terms of overhead. We have a lot more proxies running, which take CPU cycles and memory. These proxies are helping each individual application instance. All right, but there's more processes running, more context switching, more all this. So there is a performance overhead and cost to doing this. And so now, as you deploy the service mesh and start to explore a little bit more about that spectrum that I mentioned of the data plane, what should that look like? You have to think in terms of sure, resource usage and overhead is important, but so is isolation, right? One of the things that we talked about in the older models is centralizing a lot of these capabilities and some of the struggle and drawbacks of doing that. Well, one way to offset the resource overhead is to collapse a lot of those proxies down into a shared gateway, all right? But then you go right back into that direction that we're trying to account for, at least. So you lose feature isolation, you lose some of the abilities to extend the data plane the way a particular application needs it. The security granularity, which was once scoped down to a specific application instance, now opens up a little bit more, right? If you try to share some of these gateways. So, the sidecar proxy is sort of where we start in service mesh land. It's been implemented that way on purpose, but are there ways that we can optimize, and can we use some of the newer supporting technologies like eBPF to virtualize and give an appearance as though it's still this model, but under the covers, the way the proxies are deployed doesn't have to be. All right, so if we start with the basic, so in this model we have more overhead in terms of resources used, but we also have the highest degree of isolation. If you want to extend your proxies, maybe use WebAssembly, these types of things to inject into the applications. If your extension breaks Envoy for service A, that's not going to impact services B and C. All right, now, if there are security intrusions and vulnerabilities, if proxy A gets hacked, you're not exposing to all of the other proxies. And if you want to make upgrades, you can upgrade one service at a time without impacting other services. Another model, which relies a little bit more on the layer 4 networking, and eBPF can help out quite a bit here, is to collapse all of the service proxies into a shared proxy, maybe one per host. And so this goes the other way. Now you get much tighter resource usage. With the CNI, you can, the applications don't even need to know that the Sidecar is there. And so you get a tighter security control over the routing, at least from the sidecar, from the application to the sidecar. But you lose the isolation properties, right? If service A needs to extend the proxy to support some bespoke HMAC type handshake for services, and you write some bug or some issue in that extension, now you're going to affect all of the services that are on that host and any of the services where that extension is needed. So there's a notion, of course, of the trade-offs and the capabilities that you might need for the services. Another approach, which kind of starts to blend these two, is maybe we don't share the proxy across all of the services running on that host, but maybe we do it per service account. So if you have multiple instances of a service running on a particular host, you can just share one single proxy for that set of services. And now you start to balance. Now you start to tune the knobs a little bit. Now you get some better resource overhead, some better isolation, but not like you would see at either of the extremes or the trade-offs that you would have to make. And even another approach is to take the proxies completely off the hosts anyway, and force all of the traffic from applications to go through these proxies that might be living somewhere remotely, maybe as a service. And so this further, allows you to pick the right trade-offs. Maybe you don't mind taking these extra hops. You need this isolation. Resource overhead, that's put on somebody else's plate now. And you're still able to implement a lot of the same behaviors that the service mesh expects. But now you run these proxies completely out of band. All right, so the data plane is extensible. It is extremely powerful. The mode for running the data plane is a spectrum. Out of the box with most service meshes, Sidecar is the default approach, but it shouldn't have to be. You should be able to optimize the data plane for your specific use cases where you might have multiple different use cases. You might need to commingle this, but at the end of the day, you want to apply security policies, traffic policies consistently across the applications. Let me pause and see whether there's any questions.
Hey, Posta, there's a general section and there's a QA one. If you hit QA, there was a question. You covered a lot of it with eBPF, but just want to give you a shot to scan through it real quick.
I see one question. When you think about project like members, and which things do you think aren't possible to change by eBPF in the Istio Envoy Sidecar? So I'm not sure what you mean by change, but there is definitely eBPF is pretty powerful, and but has its limitations as well. So you'll notice that generally when you start talking about implementing complex protocols and various application specific behaviors, that happens to be we write that code in user space. So that's where it's intended to be written. But then there are things like you refer to SOCOps and SOCMap here. Like what does the piping look like between the Envoy proxy and the application instance? Right? Do we have to go all the way through the TCP/IP stack, potentially multiple times to route the traffic accordingly? So there are optimizations that we can do with Envoy to short circuit that. And as I mentioned in some of the previous slides, we can even use that control of the networking paths in the operating system to, like I said, optimize where the proxies even run. The proxies still need to do things like HTTP2 codecs, like starting the TLS and mutual TLS connection. Some of that stuff can be offloaded to the kernel, but there's still some of those more complex scenarios that need to happen in the user space, and that will likely, need to be some kind of proxy or some kind of user space application, which is where Envoy plays a great role today. Okay, yeah, the last bit, the last section. So we covered a little bit what is a service mesh, covered a little bit about the areas where there's innovation around the data plane. Now let's take a very quick look at some of the innovation and things that can happen on top of the control plane. So in a service mesh, like I said, the service mesh is made up of proxies that handle the requests and are on the request path between applications, and the control plane, which configures the data plane to behave a certain way. Now, I want to be using Istio as an example here. Based on my experience, our experience here at Solo, I've been involved with the Istio community from the very beginning, but it wasn't clear back in January 2017 or even July 2018 when Istio hit 1.0. It wasn't clear which service mesh was going to be, the dominant. I don't want to say the winning, but the dominant service mesh. But you fast forward through some ups and downs, some hiccups, I would say, at least on the Istio side and the Linkerd side, and all of these, right? It takes a while to mature a service mesh. Linkerd ended up rewriting their entire service mesh from scratch. But so it takes a while to mature. But I think you fast forward to around January 2020. That's when we noticed that, at least at Solo and just working with people in the market, that's when we noticed that Istio had matured at least to a point where people are confident deploying it and deploying it at some serious scale. So back in 2020, we talking with our people in the community, talking with our Solo customers, up until then, it was always, we're going to evaluate these 5 different service meshes and we'll pick the best one for our use case and so on. But right around January 2020, we were seeing Istio. People had picked Istio and were deploying it across 50 clusters, 80 clusters, and so on. And then fast forward from about 2020 to now, and that effect is just doubled and quadrupled and continued to grow. So I'm going to use Istio as the example for these service mesh diagrams, because that's the one that in 2020 is when we saw the market converge. That's when we at Solo decided to take the way we were looking at the market and focus it on Istio, and that's the most dominant, most mature service mesh out there right now. But so Istio has a control plane and a data plane. The data plane is based on Envoy, and you use a declarative configuration format. So in Kubernetes, this would be custom resources to configure the control plane. And then the control plane goes and configures the individual data planes. Now, when you start to deploy this on one cluster or multiple clusters, especially as you start to get up to multiple clusters, the configuration format for Istio, at least, and most of the other service meshes is pretty low level. It's very detailed, it's very fine grained, and it's pretty low level. So you can get some expressive policies that you can apply or define there, but it's pretty verbose. And when you start to deploy things across multiple clusters, maybe these clusters are heterogeneous. They're not running exactly the same services that every other cluster is running. Some are running in a public cloud. Some are running in a compliant zone, then the security policies, the failover policies, the traffic routing, they're necessarily different between these environments and between these clusters. So the control plane is giving you lots of knobs and switches to be able to fine-grain control your traffic and secure your traffic. But making sense of this at scale and operationally, that's where at least we've seen when people are deploying this, that they need an additional abstraction. They need an additional way to reason about and simplify the capabilities that they want to use in the service mesh. Right, and so without there are very few outlying examples. Almost all the people who've deployed Istio specifically or a service mesh at scale have built some mechanism to manage this across multiple clusters. And at least the way that we see it, and all of the examples that we've seen, it's pretty bespoke. There's a lot that goes into it. It's sometimes very, very organizational specific. But the problems that they're typically trying to solve are around consistency of policies and tenancy. How do they expose the capabilities of the mesh to the various groups, the various developer teams that need to deploy their applications and need to have these shared policies, defined. The last bit that we've noticed in the market is this idea behind unifying the APIs that you use for traffic routing and these shared policies, regardless of whether they're at the edge where people might use an API management or API gateway, or in the mesh where services are communicating directly with each other. At the end of the day, these are all services and these are all APIs, whether they're outside of your environment or inside. And the API used to configure the traffic, configure the security policies, and enable and get the consistency should be the same. You shouldn't have one API for this, another API for that, more APIs for this and the other. They're enforcing the same types of policies, so the APIs should be unified. Now, doing this, and what we've seen from various organizations, is it allows folks to simplify their mental model about what's happening. All this stuff under the covers, Kubernetes and CNIs and service mesh and proxies, all this stuff, they don't have to worry about that. They just need to focus on what is their role in the organization as a developer, as an SRE, as a platform owner. Write the policies that they care about, enable the tenancy that they might need so you're not stepping on each other, enable the hierarchy that you might need because platform team might need to enforce specific policies, and do that in a way that's declarative and understandable. So you can look at the intent, you can understand the intent of what the system's trying to do, and not go off into, well, we have these scripts over here and these really low-level APIs over here, and maybe we put this resource over there on that cluster. I don't know, right? So you need to add some level of management to infrastructure like this, and this lives on top of the service mesh control planes. All right, so building that model lives on top of those control planes. Yep. Well, all right, and so I talked a little bit more about the models and the approaches and what we're seeing in the market and with our customers in the open source community. I can leave these slides behind, but this is exactly the problems that we're solving, bringing GraphQL, bringing eBPF to the solution, and unifying the various layers of the networking stack so that we can simplify a lot of this stuff. It's sprawl and complexity is a big problem in customers that we work with, and that's definitely what we're trying to help solve. That's all I had. I can show a demo. I'm happy to take Q&A, either on the chat or live if people want to jump on.
Yeah, so if you do have questions, please put them in the chat. Yeah, let's see. If you would, how about this? If you'd like to see a demo, give a thumbs up. Here,
I also recently published my book, Istio in Action. Came out, I think, last week or the week before. That's a picture of it actually on my countertop. So it is a real thing. It was hard for me to believe because it took 3.5 years to write it. Eric Brewer, who's a very well-known Google fellow, author of the CAP theorem papers and all that stuff. He wrote the foreword to the book. If you're interested in Istio and going in a level lower, it's got something for beginners, intermediate, advanced users. So I put a discount code there. I think that still works.
All right. Yeah, looks like we got a few thumbs up for a demo. And definitely, if you're interested in this in the topic Istio in Action, I'll post that in the event wrap up as well. If you didn't get a chance to snag it right now, I'll let you hit the bring up your demo environment, and let's take a look at it.
Yeah, definitely. Okay. All right. So I'm gonna show exactly what I was just describing. Let me see if I can find. Actually, you know what? I have the slides here. What we're gonna look at is this. We're gonna take a look at a couple Kubernetes clusters that are running some workloads. If you're familiar with Istio, you should be familiar with the BookInfo demo. Basically, just a web page that shows information about books. And depending on which version of the services you hit in the back end, you see different results or different data about the book. But we've deployed it across a couple different clusters. And the concept of this unifying API for north, south, and east, west traffic, I'll show the concept around tenancy and kind of bounding your configuration and security properties to a specific set of namespaces and clusters. So the workspace concept that we have allows you to carve up basically a the deployment of multiple clusters of Kubernetes or VMs, and pick specific namespaces in those clusters that belong to your tenant. So yeah, and the last bit is that all of this, all of the stuff that I'm going to show plugs in very nicely with a Git based workflow, which we believe, I believe, is extremely important. And what we've seen is with our customers or users in the community, that the way that they're able to build their self-service and invert the relationship. Remember I mentioned the centralized bottleneck teams. You go open a Jira or a ticket or something to go get them to change, and then maybe 3 weeks later it happens, right? They've inverted that relationship. They've enabled automation knobs so you can go do it yourself and do it in a way that has guardrails and that does have some audit approval and stuff where needed, but much more self-service enablement. A lot of that is GitOps forms the foundation of that. So I think this is the slide, or ultimately what we'll be looking at is how to carve up different parts of the cluster and hand that out to different teams and get consistent security and traffic routing policies across an environment like this. So the first thing that we are going to take a look at is I have, if I do KTX, I have 3 different clusters as I illustrated. I don't know if you can see in the bottom left-hand corner. Cluster 1, cluster 2, and the management plane cluster, which aligns with the diagram I just showed. If we look, let's go K9's context, cluster 1, we can see that I have the BookInfo demo deployed in cluster 1 and cluster 2. If I look in, let's pick the BookInfo backends, we can see we have some services deployed here. 2 different versions of reviews, V1 and V2. And on the second cluster, on the second cluster, we actually have 3 different versions of the review service. And I'll show you, let's see if we log into our machine here, what the BookInfo demo looks like. So if let's refresh a couple times, we should see, shows some book details, some reviews about the book. If I refresh a couple times, you should see that the traffic will load balance across a couple different implementations of reviews, right? But we see black stars and we see no stars. That's versions 1 and versions 2. If I refresh enough times, we still are not seeing version 3 because traffic is pinned right now to cluster 1. We happen to go into cluster 1 and the client is maybe geographically pinned, let's say, to cluster 1. So if we look at the policies that have been deployed, we can see we have our 2 clusters that our management plane is registered with. We can see we have 2 different workspaces. Again, the workspace concept is a unit of tenancy. And we've deployed some configurations into our BookInfo tenant. The gateway tenant is actually an administrative tenant. The gateway tenant deploys our edge ingress gateway. And that tenant could be responsible, you could think, for exposing APIs on the gateway, setting up TLS and TLS termination, doing all that integration, you know, and having some control over the ports that get exposed, protocols that get exposed. But then how routing actually happens, the gateway tenant doesn't want to be the sole owner of that. So we want to delegate that to other tenants. So I click on the gateway tenant here, we can see that we've actually imported the routing tables from our BookInfo tenant. So if in BookInfo I specify some routing rules, those will automatically get exposed at the gateway level, which all of that stuff is in place. If I take a look at Argo CD, we look at the BookInfo job. Actually, let's just go to Git. We'll go to Git and take a look at the BookInfo repo. And we can see we do have our routing table, which specifies, you know, route traffic basically to the product page service, which then that goes and calls some of the other services. Now, what if we wanted to implement rate limiting on this service? So what we can do is we can specify a rate limiting policy, right? This rate limiting policy, and there's some other configs in here where we can say how many times per hour or whatever it is. But the interesting bit here is we can specify, in this case, a rate limiting policy. Or we can specify other things like failover policies or extension policies or whatever. The model is basically define a policy, and then how we apply it to specific routes or services is through labels. It's extremely flexible and follows you know, the same models that you would expect in Kubernetes. So any of the routes that have rate limited true, at least in this case, very simple demo, this could be, you know, rate limit is gold level or platinum level or whatever. But in this case, we'll just enable it to true. Rate limited is true. then we should expect some rate limiting behavior. And this can be for traffic coming into the cluster. This can also be traffic in the east-west direction, service to service, or maybe even crossing clusters. All right, so to implement this, let's go find our routing table. Let's find our routing table, and we're going to add that rate limited is true to our routing table. We're going to do that hopefully from here. Go in here, find our route. Oh. Rate limited is true. All right, now we're going to write that. Get status. We see that. Get add. Get commit. All right, and we push this to our GitHub repo, or Git repo in this case. If we refresh, we should see, indeed, we do have that label now. And now we have to do whatever promotion or whatever the workflow is to get it into the production environment. Oh,
Christian, can you increase the font a little bit?
Yes, absolutely. Here, let me increase it over here. You should be able to see it a little bit more clearly here.
Yep.
All right, so we've added the rate limited labels on Argo. If we do a refresh real quick on this workspace, we should see that we're out of sync because we just pushed a commit to Git. What we want to do is we want to sync that config down to the clusters. We'll give that a second to sync down. Running in a VM here on my machine, so it's possible it's a little slow. We'll give that a second to sync, but let's get the product page response. We're going to call the product page a couple times and just look at the headers. We can see that we're seeing HTTP 200s. If we come over here, we see that it is synced, hopefully. It says it's syncing, but it says it's green, so I'm going to assume that it is. Now let's take a look at the way we're going to call this. We're going to call this down here, this curl. Here, let me just do this. Hopefully you can see this. But we're going to curl it with specific headers that the rate limiting service is looking for and saying, hey, if I see these, I'm going to count them. And if I exceed a count, I'm going to rate limit the request. All right, so since we added that label and we're watching for those headers, let's call it. We see that worked. And if in this case I set it to one per hour, but you can see now that the traffic gets rate limited as we would have expected it. And now this happens to be on the traffic coming in, but this could be for any of the services where rate limited is true as part of the labels. Now the last bit that I'll show here is when we're running here and we refresh a couple times, like I pointed out earlier, we're running and we're seeing reviews v1 and reviews v2 because we're calling into cluster 1, we're kind of pinned to cluster 1. But if I come over to cluster 1 and I take down the product page service running in cluster 1. All right, so now that doesn't exist. Now when the client calls into cluster 1 looking for product page, it's not there. What we should see is automatic failover to the other cluster, to cluster 2. And that configuration is specified in what's called a virtual destination, where we can specify a host, a globally aware host name. So this could be productpage.solo.io. In this case, I just have it as .global, but it could be a fully qualified domain name. And then whenever traffic comes in, we would route to that name. Well, under the covers, if there's no local endpoint, the service mesh will automatically figure out where is a running and healthy endpoint, either based on priority or based on locality, and automatically route the traffic over there, even though it might be unhealthy or not working in the current cluster. So if I click refresh, we should cross our fingers. Oh no! All right, it did fail over because we got a response. If I refresh a few times, we should see load balancing between black stars, red stars, which is only running in cluster 2, and no stars. So we should see that we get the load balancing behavior. But now we see the traffic is going to cluster 1 and then immediately failing over to cluster 2 because the product page service is no longer running there. And so that's just again an example of what this higher level API looks like. Well, multi-tenancy, when you adopt a service mesh, the things cognitively that you should be focused on are what are the things that I need to do as a developer? I need to specify routing rules, or as a SRE or as a platform team, I might want to specify fault injection. I might want to route a certain percentage of traffic to new versions of a service. Now, how do I do that across multiple clusters in my own tenant, my own environment, where that could span a lot of clusters, a lot of different namespaces, and so on, without stepping on other people? And that API should be valid for both edge and ingress use cases, as well as east-west use cases. That's all I have for the demo. Yeah, happy to take questions.
All right. No, don't you remember the days when all you had to worry about is can I get this thing to run on Windows? It wasn't multi-pods everywhere.
Yes, and even that didn't work out all that well.
Yeah, for sure. Yeah. So if there's questions, please bring those in. There's one in the chat. I'll read it out loud, so it'll be on the recording from AJ. Has there been any security events like hacks on the Istio service mesh?
So as I've mentioned, Istio and Envoy Proxy specifically is in the request path, is on the data plane, and there are, periodically there are CVEs raised against Envoy that go under an embargo situation, and we try to patch that as quickly as possible, and then release unembargo the CVEs with the right patches and everything. Here at Solo, we are on the product security working group in Istio, so we do see all of those CVEs that are coming through. We do patch them. At Solo, we do have supported versions of Istio as well that are hardened and support N-4 backward patching for CVEs. So we do take the fact that there are vulnerabilities in software very seriously, and we do what we can to backpatch all of those affected versions. So the answer is yes. Just like any software, there are vulnerabilities that crop up, and there's established process, not just in Istio and Envoy, but other software as well to handle that.
Okay, yeah. So it's the just like with other software, there's I don't think I've ever seen anybody ever write code without bugs. They're there. Yep. Any I don't remember any big news stories about, hey, this somebody got breached because of Envoy. Are there any of those types of stories out there, or it's been pretty calm so far?
There aren't, not that I know of a big security breach that was a result of Envoy. I mean, one thing that wasn't directly affected, that an area where we did step in and help alternatively, which is that log4j shell expansion attack. So as requests are coming through Envoy, we can filter out using web application firewalling rules, we can filter out requests that don't align or that look malicious. But I don't know of a, and look, Envoy is used at scale at Lyft, at Google, at Verizon, at eBay, at our customers like SAP, like T-Mobile. And I mean, so Envoy is very, very highly deployed. And like I said, there's no question there are CVEs that pop up, but I can't think of, or I don't know of any exploits that resulted in data breach and that kind of thing.
Okay, no, that's good. I don't see any questions in the chat, but I do have a few questions. That they do ask to our presenters. And if you're still thinking of questions, please do put them in the chat. So on with Istio and what you've been doing the last few years, it's been kind of on the bleeding edge of technology. And could you I guess give some perspective on what is that like, and how do you even get into one of those bleeding edge type situations? What kind of skill set or did you think that helped bring you there?
Well, if people are looking to get into that type of environment, we are hiring, but we look for. I think having a strong foundation in containers and Kubernetes, which that itself has helped spawn, some of the next things on top of and around Kubernetes. But having a strong foundation in those in that area really helps a lot to either kind of see what's coming next, because you're working in that environment, you see what people are doing. So part of this, like when I was working at Red Hat, we were deploying things. OpenShift had just Kubernetes had just come out. OpenShift was v3 had just come out, and we were seeing people go from their VM environments to trying to bring things into this container environment. And the problems around connectivity that they were having. And so the more you're familiar with this environment, the more you can sort of see and spot these things, and that we do see that Istio service mesh has been in the past, I would say, on the bleeding edge, but the more people are catching up with their modernization efforts and they're running into these problems, the more mainstream Istio and service mesh is becoming. So yeah, I think just kind of being in the right place, right time.
That's a good point. It's it is becoming more and more mainstream. So a couple of questions from the chat. One is, what's that discount code for the book again? I can maybe type it in or flip to that.
We can put it in
that slide.
Let me put it in the chat.
Yep. And then there were a couple of questions on the Q&A tab that I'll get to. Looks like, yep. So one is a quick question. Is Istio written in C?
Istio is written in Golang for the control plane part, and C++, or Envoy is written in C++ for the data plane part. So there's no C.
No C.
It's C++, yeah.
All right, and then one more. What is the best performance you've accomplished on the data plane part? I guess it's we can take that as bandwidth or throughput. If you've done any massive performance tests at scale on the data plane, or if you haven't done them at solo, have you heard of kind of the best performance that's been accomplished there?
Yeah, we've definitely done them with our customers. So it's it's always a little bit tricky because you also have to ask as part of that question, well, what features are you using? Because there are certain things like, for example, request comes into Envoy Proxy. Now with our gateways, we have a request and response transformation filter. So if you get a big JSON blob coming in and you want to do some transformation of it,
Yep.
that's going to be a little bit more expensive. Or another one that we see, especially at the financial companies, is request comes in and we need to perform authentication and authorization. And the mechanisms for doing that include calling into one of their already existing services for doing auth and auth. And so, or rate limiting, calling out to the rate limiting server to figure out counts and whether or not things should be. So the more capabilities you add, the more latency, reduction, throughput, saturation, that kind of thing that you'll see. But we can say very confidently that, let me give an example. An actual use case at a large financial institution that was looking to modernize their API gateways to start off with, and then move to service mesh. They were running what I guess I'll just call a legacy API management product. And what they were seeing in terms of requests per second, or they actually cared more about latency. They're a credit card company, processing company, and they care very much about putting bounds around latency. But the numbers that we saw at like P95 or P99 for latency in the legacy product was something on the order of 200, 250 milliseconds.
All right.
But this is, I mean, it's doing a lot of stuff, doing rate limits, doing authentication, authorizations, doing request transformation, all this stuff. But we put that into Envoy and Glue Edge, and we were able, it took some tuning. Things don't just magically work out of the box, but it took some tuning. And we were able to tune that P99 for a highly loaded API to 8 milliseconds. So obviously C++ being pretty performant helps out. But then, the various knobs and switches that you can use to tune Envoy proxies, there's a lot of it. Now, if you're talking about in the service mesh use case, we can tune Envoy to, a level of like a millisecond or 2 milliseconds of overhead, at the worst case at P99. So, I mean, it really depends on the scenario, depends on whether you know how to tune it, which we do. Yeah, we can get good performance out of it.
All right, cool. One on the book, looks like Wences might be a O'Reilly Media subscriber. Do you know when this book will show up there?
That's a good question. So it's a Manning book. If you can get other Manning books, like say Kubernetes in Action, on the O'Reilly Media subscription, then I would imagine this will make it there eventually as well. But if you cannot get Manning books on that, then it's probably unlikely that this will make it there.
All right, and one final question. This is if you could go back in time and talk to young Christian, what advice would you give your younger self at the start of your career? Now, it's not fair. You can't bring the book of who wins the Super Bowl, so you can bet on it. But what kind of tech career advice, or even just general career advice, would you give yourself, your younger self?
Oh man, that's deep. I don't know. One thing that I may be a little unusual in the tech field, I don't know. But one thing that I've done is I've taken risks, I've taken chances, moving from jobs to other jobs when it was the right time, but I didn't know it was the right time at the time. So being open to being a little uncomfortable has actually been, something that I didn't proactively think about it at the time, but that has been good. It has turned out good. It didn't, anytime you take a risk, just a chance it doesn't turn out good. But so far, it has. So being a little adventurous, being a little, taking some risks is good. But I don't know. I don't know what I would change. I've been pretty blessed, to be honest. So yeah, I don't know how best to answer that.
No, that's fine. Anything you tell yourself is good, and just maybe don't be taking risks. There'll be some unease about it, but and obviously you have to go into maybe picking the right risky thing
Yeah.
to go into. Like you don't want to jump into or if you do take a risk and it doesn't turn out right, to be able to adjust from that and
To go back, exactly.
go back. Yeah.
Yeah. Yep.
All right, Christian, really appreciate the time that you spent with us. It's been great having you. Thank you for carving out part of your time to talk to our group here about what used to be the bleeding edge, now becoming less bleeding edge, but still bleeding edge for most people.
Yeah.
Yeah, it's really great.
It's my pleasure, absolutely. And thanks for having me.
Yeah, give the golf
Hopefully to
clap.
do it in person one day.